Welcome to this introductory lecture on methods for high-throughput computational screening. I'm Dave McDowell, Regents Professor and Carter N. Payden Jr. Distinguished Chair in Metals Processing at Georgia Tech in the Schools of Mechanical Engineering and Material Science and Engineering. As learning outcomes of this discussion, we'll first consider distinct classes of models expressed at different length and time scales corresponding to different scales of hierarchy of material. Secondly, we'll distinguish between materials design and multi-scale modeling, two different pursuits. We'll talk about materials discovery versus materials development. And finally, we'll close with a discussion of computational methods for materials discovery, in particular screening of materials. There are distinct classes of models that correspond to different length scales and time scales of material behavior, all the way from the quantum mechanical level, individual atoms and particles and subparticles, up through the continuum representation of materials and structures. And you can see that these models span from angstroms to meters in length scale, and from femtoseconds, the scale of atomic vibration, to the time scale of years in applications. And as we move from lower left to upper right, we move from a dynamic description into a smeared continuum description. And we move into the territory of engineering models, meta-models, surrogate models. It's important to distinguish multi-scale modeling, shown at the bottom here, from multi-level materials design. That is, knowing the performance requirements, can we determine what the appropriate material properties are, and from those properties can we determine the structure, and then can we estimate what process path histories or synthesis routes are necessary to achieve those structures. That's a top-down design approach, which is very familiar in engineering design, not so familiar in materials design and development. It's important to consider that these two are not equivalent enterprises. Multi-scale modeling in particular supports multi-level design of materials at every scale: process, structure, structure, property, property, performance, at every stage of the process. Now, we can also distinguish between nanoscale design and microscale design, and of course you're familiar with macroscopic design of components such as golf clubs and automobiles. And let's turn our attention down to the nanoscale and consider nanoscopic or molecular design. This type of design is applied to specific molecules, for example, HIV drug virus blocking that is used to guard against or to prevent HIV, and various types of algorithms for designing at the molecular or atomic scale structured materials that have certain required functionality. This is normally supported by atomistic models or even first principles quantum mechanical models. On the other hand, we can scale up a bit and go into the realm of microscale design, which considers on the order of maybe tens of nanometers to micron scale, considering the structure of materials, the so-called microstructure of materials that gives rise to a lot of important properties, collective ensemble properties. These sorts of approaches are a little bit different, and they require not atomic scale modeling, but typically modeling such as continuum finite element or phase field modeling to support them. If we think about the distinction between streams of materials discovery and development, as I had mentioned in a previous module, discovery is related to the aha moment of first encountering a new material, whereas development is related to how we improve that material, how we go through the steps of property optimization, certification, manufacturing scale-up, etc. So the discovery phase is very much focused on calculations, computations, first principles approaches, quantum mechanical approaches, atomistic modeling approaches, computational thermodynamics, so density functional theory codes, thermodynamic databases. This is the stuff of discovering new materials, sequencing through large sets of options and exploring candidate material solutions at the nanostructure. On the other hand, development asks the hard questions of how do we fabricate these structures, how do we scale them up so that when they're assembled at larger scale, they deliver the required property requirements and are stable in required performance applications. As an example of the materials discovery high throughput screening based on computation, I would advise you to check out the Materials Project website shown at lower right, which is a very interesting and, in fact, fascinating study of how materials are screened for functionality using density functional theory calculations, thermodynamic databases, and so forth. In fact, at this site, you'll find information about battery materials, functional materials, structural materials, all explored or screened for potential candidacy to serve in a given application based on these kinds of first principle models. New compounds are discovered every day that have not been previously made in a laboratory using these kinds of methods. One can also script the workflows for this discovery process by simply connecting the elements of computational strategy to be able to do parametric studies, comprehensively explore the relationships between stable structure of materials and compounds, and their properties for candidate performance requirements. And again, you can find this in the Materials Project website. As in another example, you can look at the work shown here by Kirkin, Meredig, and Chris Wolverton on high-throughput computational screening of new lithium-ion battery anode materials. And this work uses density functional theory and explores in an automated way using ground state thermodynamics candidates thermodynamically stable lithiation reactions. You can also consult this work that considers the high-throughput highway to computational materials design, a very intriguing idea of how one can use combinatorial searches through the high-dimensional structures based on first principles that can give us insight into which of these compounds or structures should be most useful to synthesize in the laboratory and explore further in terms of providing candidate solutions. So this is the stuff of materials discovery, new materials development in a high-throughput context. And again, we distinguish this from the high-throughput nature of development, which has to do largely with experimental methods. So in summary, there are distinct classes of models employed at different length and time scales. We have availability, access to these models now. And we must distinguish, though, between goals of designing materials and developing materials and multi-scale modeling, with the latter providing support for materials design. Finally, materials discovery differs from materials development in that it employs screening strategies based on predictive first principles approaches to look at stable structures that may have the potential to deliver candidate property sets that are required for given applications. Elements of metastability, structural stability, kinetics are all elements to be added to the mix in scaling up the problem to the materials development. With that, I close. Thank you very much.